So, hello everybody. Today we are in the second class to discuss the double pipe heat exchangers. So, in the last class we had discussed the general arrangement of the double pipe heat exchanger. It is a concentric pipe arrangement, and all these concentric pipes, they are arranged one above the other in series. They can also be in parallel arrangement, and in this particular case each particular hairpin, it comprises of two pipes connected by a return bend, that is known as one particular hairpin. And we had started discussing the design. We had discussed the heat balance equation and also the rate equation, and in this particular rate equation we had taken up each and every term and we had started discussing. Our initial discussions were on the log mean temperature difference, right. Once we know how to find it out for different cases, now we come to discuss the overall heat transfer coefficient. You might recall that in your introduction class to this module 2 on heat transfer processes, then the general equation was derived for the overall heat transfer coefficient, and it was said that the overall heat transfer coefficient, this can be defined either in terms of the inner wall of the inner pipe, or it can be, for example, it can be defined in terms of the inner wall which has a diameter. Again, if I just draw it out here, this is the inner pipe and this is the shell, or rather it is not the shell, it is the outer pipe. We call it a shell in a shell and tube heat exchanger. So, therefore, this is, again I will mention, this is d I, the outer diameter of the inner pipe is d O, and the inner diameter of the outer pipe, that is d I O. So, therefore, you can very well see that the heat transfer coefficient, it can be defined either in terms of, as it was mentioned, either in terms of the heat transfer area of the hot fluid or in terms of the heat transfer area of the cold fluid, right. This derivation was also given to you here. The HH, this is the heat transfer coefficient of the hot fluid, the area occupied by the area of heat transfer on the hot fluid side. This is the heat transfer coefficient of the cold fluid, the area of heat transfer on the cold fluid side, and this is basically the resistance offered by the metal wall, and this is again the, since here it has been defined in terms of the heat transfer area of the hot fluid. So, therefore, RW is multiplied with AH. Now, if we apply this general overall heat transfer coefficient equations to the specific case of a double pipe exchanger, then in that case generally as I have already mentioned, that the heat transfer area is taken as the outer wall of the inner pipe, or in other words, the area of heat transfer is A0, which is given as pi into D0, the diameter, the outer diameter of the inner wall, into the length, the total length which will be required, right. And this is obtained as Q by the, since this is A0, so therefore, U is defined as U0 into delta T LMTD. Delta T LMTD will not talk much. How to find out this U0? Because moment you can find out this U0, you can find out A0. If you either find out D0 or you select D0, you find out L. At some conditions, you select both D0 L, find out the number of hairpins, whatever it is. So, the standard equation from here, if we just write it down with consistent nomenclatures, in fact, this was also mentioned to you in your introduction class, then U0 you find it is a function of heat transfer coefficient of the outer fluid, heat transfer coefficient of the inner fluid, the outside diameter of the inner pipe, inside diameter of the inner pipe, thermal conductivity of the wall between the two. Now, here I would just like to mention one thing, that heat transfer tubes, they are slightly different from the normal pipes. In normal pipes, when they are specified by the nominal diameter, which is neither the inside nor the outside diameter. It is a notational specification. In heat transfer tubes, when we say nominal diameter, it refers to the outside diameter of the tubes. There is also one other thing that you will be remembering. In pipes, there are two things that we specify. One is the nominal diameter, the other is the thickness. The thickness is defined in terms of schedule number. Higher the schedule number, thinner is the pipe. In case of heat exchanger tubes, we define the thickness in terms of a Birmingham wire gauge or the BWG. So, therefore, heat transfer tubes or the heat exchanger tubes, we just cannot select normal pipes for heat exchanger tubes. This I just wanted to mention before we go for the details of the design. So, therefore, for UO, more or less you need to find out Kw if you have selected the material of the of heat transfer, Kw you know, HO and HI are the two things that you need to find out. Now, if you remember again in an introduction class, there were different correlations which were proposed for finding out HO, for finding out heat transfer coefficient. The same correlations can be used for finding out HO and HI. There are different correlations, but remember most of the all the correlations, they have a generalized form which tells you that Nusselt number is a function of Reynolds number and Prandtl number. Prandtl number is a property group. Reynolds number comes since the two fluids are flowing. You will remember Reynolds number comes for pressure drop, Reynolds number comes for finding out Nusselt number, Reynolds number is also present for finding out Sherwood number. So, this is a common thing. So, therefore, the different correlations they are provided here. For turbulent flow, mostly they are turbulent flow. So, therefore, this is the correlation, and it is also mentioned that for double pipe often we use 0.023. Intermediate range also the correlation is given. For the laminar flow also the correlation is given. Now, for finding out H, what are the things that you need? You need to know K, you need to know mu, you need to know Cp, right. If you have seen the problem that I had given you, the mu was specified over a range of temperature, and you will find that mu is quite a significant function of temperature. Even if your K or Cp, they do not change much with temperature, but mu changes with temperature. So, under what conditions are you going to evaluate these physical properties? This I had mentioned in the beginning of the previous class when I had shown you the design problem which you are supposed to work out as we progress with the discussions of the design. Remember one thing, for both the inner and the outer fluid, the properties should be evaluated at the average temperature, which is nothing but T in plus T out divided by 2. Now, there is one other thing also which I would like to mention. Suppose it happens that the wall temperature is much different from the bulk temperature. Under that condition, we find that the viscosity of the liquid at close to the wall will be different from the viscosity of the bulk liquid. And under that condition, we require another additional correction term to the standard equation for Nusselt number. This particular term, this was first proposed by Tate. So, therefore, this is known as a Tate correction factor, which gives you that whatever H you are going to get from this equation, that needs to be corrected by a mu by mu w, where mu is the viscosity of the fluid under bulk conditions, and where this mu can be evaluated at T average, and mu w is the viscosity of the fluid under the average wall temperature. So, therefore, what you need to do for this, you need to find out the average wall temperature. It is very simple that if this is the wall, and here what do you find in this particular case, again from the heat transfer equation, if you find that more or less on this wall, on one side say the inner fluid is flowing, on the other side say the outer fluid is flowing, right. So, therefore, for this particular fluid what is Q equals to, this is equals to HI AI, and heat transfer is occurring say in this direction. Say for example, the inner fluid is the hot fluid. We just assume, does not matter even if you assume the outer fluid to be the hotter fluid, the derivation in no way it is going to change. So, therefore, the average temperature here is Ti average minus T wall, right. The heat is going from here to here. So, therefore, in this particular case Q equals to HO AO again TW minus TO average. TO average will definitely be given by TO in plus TO out by 2, TI average will be given by TI in plus TI out by 2, right. Now, whatever heat it's being given out by the hotter fluid will be taken up by the cooler fluid. We assume that there is no heat transfer or the entire heat is transferred between the fluids at their average temperatures. So, therefore, we can equate these two. Once we equate these two, what do we get? We get HO AO TW minus TO average, this is equal to HI AI TI average minus TW. And we know how AO and AI they are related. AO is equal to pi d0 L, AI equals to pi DI L. So, therefore, AO by AI equals to DO by DI. So, therefore, you can replace one with the other by just substituting by DO by DI. If you perform this particular derivation here, then you will find that, let me see if there is little more space here. Yeah, I can do it here also, or else I can do it here. So, therefore, in this particular case you can find out that Q this is equal to, I will just write out once more and I will do it, HO AO TW minus TO average, since the outer fluid is the cooler fluid, this is equals to HI AI TI average minus TW. So, from there if you equate these two, then and then you can write it down as HO AO plus HI AI TW, this will be equal to HO AO, you can do it yourself itself, plus HI AI TI average. Now, for for these AO you can replace them with AI DO by DI. Here also you can replace it with AI DO by DI, and then if you substitute all this, then in that case you can get an expression of TW which is given in this particular expression. So, you can work it out yourself. You find that under this condition you get the average wall temperature. So, therefore, what you are required to do, because this is an iterative process for finding out H, you need this, and for finding out mu W you need TW, for finding out TW you need to know HI and HO. So, what is the process that is used? To start with, you assume mu by mu W equals to 1, right. So, initially what we do, we assume mu by mu W equals to 1, and once you can assume this, you can find out this particular Nusselt number and you can find out H. After you have found out H, you can find out in the same way, you can find out HI by assuming the inner fluid by W equals to 1. Same way you assume mu O by mu W 1, you find out HO. Once HO and HI they are found out, then you substitute these two, find out TW. Once you have found out TW, you can find out mu W. Now, you can evaluate mu by mu W, and then again you can find out HI and HO. Normally, we find that one iteration is usually sufficient, we do not have to go for further iterations here. So, therefore, in this particular way you can find out HI, you can find out HO, Once you have found out HIHO, you can find out UO. There are certain other things also which I would like to mention. Other than the properties, there is an equivalent diameter or the equivalent characteristic dimension of the heat transfer surface which needs to be incorporated. Now, when you are working with the inner tube fluid or when you are working with, we are trying to find out HI, then in that case it is very simple. Your effective or equivalent diameter is nothing but the inside diameter of the tube. When you are working with the outer pipe, then in that case the outer fluid, it is flowing through the annular area. We all know that for any annulus, for single phase flow through an annular area, the equivalent diameter is usually defined as the hydraulic diameter, where the hydraulic diameter is 4 times the hydraulic radius, and the hydraulic radius, it is defined as the wetted or rather cross sectional area divided by the wetted perimeter. So, therefore, in this particular case we know what is the wetted area. It is naturally pi do square minus pi dio square minus do square, is not it. So, therefore, the cross sectional area which is occupied by the annular fluid. And what is the wetted perimeter? The outside wall is also wetted. If you find here, for the annular fluid, this wall is also wetted and this wall is also wetted, right. So, therefore, the wetted perimeter, what it should be? It should be pi dio plus do. So, therefore, in that particular case, this is going to be pi O plus do, right. So, therefore, from there what do you get? You get that for the annular fluid, the dE is nothing but equal to dio minus do. We can use this, and for the inner fluid you can use this. Now, here I would just like to mention one thing. This was pointed out by Kern, and since we have been referring to the book by Kern, it is important for you to remember that what Kern had suggested is that he said that, well, this definition is fine as far as you are going for finding out the pressure drop. I have no problems. But when you are finding out the heat transfer coefficient and you are defining the equivalent diameter under that condition, then it should refer not to the wetted perimeter, but to the perimeter through which the heat transfer is occurring. So, he said that for heat transfer case, the RH, it should be defined. In fact, this is 4 RH that should be defined. This should be defined as pi dio square minus do square, this is the cross sectional area, divided by pi do, since the heat transfer is occurring through the wall of the inner pipe. So, according to him, he suggested that the equivalent diameter for heat transfer, or in other words, the equivalent diameter which is used in this Nusselt number, in this Reynolds number, they should be calculated by using this. And when we calculate the Reynolds number for finding out the pressure drop, under that condition we should be using this. Anyhow, for our case, we take up this particular definition of the equiperiphery diameter to calculate Reynolds number for both pressure drop as well as heat transfer coefficient. We take this up to calculate also the Nusselt number. We take up this particular definition also for calculating the friction factor. We use the same thing. Well, this was regarding the hydraulic diameter. Now, the thing is that if we really want to use these equations, we first have to define the inner fluid and the outer fluid. We did not discuss it earlier, but when we go for design, after we have decided the heat transfer equipment that we are going to use, that definitely we will be deciding based on the heat transfer load and also the heat transfer area apart from other considerations. After that we decide the inner fluid and the outer fluid. There are few guidelines that I have put up here. These guidelines, they are common both for double pipe exchangers as well as for shell and tube exchangers. So, therefore, whatever I am going to discuss regarding which fluid preferably will be on the outside and the inside will also be applicable regarding which fluid will flow on the shell side and the tube side in the shell and tube exchanger. There is another very important thing that I want you to remember. These are simply some guidelines and they are nothing sacrosanct, and mostly we decide on the inner and the outer fluid based on the application, based on the conditions at site, or based on heuristics, based on previous experience as well. These can just be used as guidelines when you decide regarding the inner and the outer fluid. Certain things they are coming from common sense itself, so therefore, there is not much discussion on it also. Let us take up one by one and see that where will you prefer to put this particular fluid under generalized conditions. Say for example, corrosive fluid. It is quite evident that if you put the corrosive fluid on the shell side, then what happens? Both the shell as well as the inner wall of the shell and the outer wall of the tube gets corroded. You would definitely not want that. The other thing is, if you take up the corrosive fluid and put it on the tube side, then it is easier also to clean the tube, and the other thing is it is easier to replace the tubes. Tubes are mostly bought out items, so that you can very easily replace them. In fact, you can take out tubes without even opening the shell. So, naturally, if the tube inner surface gets corroded, it is at least better. So, therefore, it is more preferable as compared to the shell side, rather both the tube outer surface and the shell getting corroded. So, therefore, we would prefer to keep a corrosive fluid inside the tube. Same way, more hazardous fluid. Definitely, when you are working with a more hazardous fluid, you would not want the fluid to leak out, right. If it is in the shell, then there is every chance or a greater chance of leakages through the space between the inner pipe and the outer pipe. We put gaskets etc., but then also there are chances of leakages. So, naturally, when we go for hazardous fluids or when we go for more expensive fluids, we would prefer to keep it on the tube side. What about dirty fluids? Dirty fluids means maybe fluids which have some particular solids. These solids, they can get deposited, or maybe fouling fluids which foul the tubes. For these particular cases also, we would like to keep them on the tube side for certain reasons. First thing is, it is easier to clean the tube inside surface, number one. Next thing is, while flowing in the tube, there are lesser areas of stagnation points, right. The flow is much more uniform. So, therefore, when there are lesser stagnation points, there are lesser areas where the fouling fluids can accumulate. This is the reason why generally cooling water is the most common coolant that we use. Cooling water is generally, rather it is generally the tube side fluid for this case. Second thing is, suppose there are dirty fluids which have got some solid deposits etc. The thing is, inside the tube diameter is lower as compared to the shell, rather the outer pipe diameter. When the tube diameter is lesser, naturally the velocity of the tube side fluid will be higher. When a fluid is flowing at a higher velocity, chances of depositing the solids etc. decreases. So, therefore, for this particular reason again we prefer slurry to flow in the tube side fluid. The other thing is fluid at a higher pressure. In this case also, if you remember that I had told you that when a fluid is at a higher operating or a higher design pressure, under that condition, if you remember, the T, this is equal to P d by 2 sigma. So, naturally we find that since the diameter of the P is of the tube is less, then quite naturally it can withstand a higher pressure. This I have already discussed. This is the reason why double pipes are preferred over shell and tube exchangers, and this is the reason why the fluid at a higher operating or a design pressure is preferably introduced through the tube side. Now we come to the more viscous fluid. Where will you like to keep it? Now remember one thing, in the shell side, if you remember, the critical Reynolds number for the shell side or the outer tube, this is near about equal to 200. While on the tube side, Re critical on the tube side, you know very well, this is around 2100. So therefore, we find that the chances of having a turbulent flow and therefore greater mixing, that is more on the shell side as compared to the tube side. So therefore, when we have a more viscous liquid, in order to ensure that the flow is turbulent, we would like to introduce on the shell side. But remember one thing, if the fluid is so viscous or the velocity is so less that even in the shell side it exhibits laminar flow characteristics. Under that condition, in order to increase the velocity, we would like to introduce the fluid on the tube side. Well, the next is, suppose a fluid is undergoing a phase change, say maybe a fluid which is vaporizing and with the latent heat it is heating up another fluid. In this case, what happens, as phase change occurs, the two phase flow, it has got a higher pressure compared to the single phase flow, and also when vapor is formed, you need some space for the vapor to accumulate. It is easier to provide this space in the outer tube or in the shell side. So, for fluids undergoing phase change, we would like to introduce them on the shell side. Now, the next thing is when the fluid has a higher temperature. Quite naturally, if you have observed that whenever we are doing any derivations in the introduction, here in this particular class, we had always mentioned that let the hotter fluid flow through the tubes. The reason is very simple, because if the hotter fluid flows through the shell, then we have to provide an insulation to the cell. There are chances of greater heat loss if the high temperature fluid is flowing through the shell. This is number one. The number two is that whenever the temperature is higher, then naturally what happens, the yield stress that decreases. So therefore, since the tubes they are having a lower diameter, so therefore chances of withstanding a higher pressure at higher temperature is more for the case of the tube as compared to the shell. So therefore, higher temperature fluid we would like to put it in the tube side. When the fluid has a poorer heat transfer characteristics, or in other words the H is low, then in that case if you put it on the shell side, what happens, the critical, as I have told you, the critical Reynolds number for the shell side fluid or the outer fluid, it is 200. So, chances of attaining turbulent flow is higher. So, therefore, improved heat transfer characteristics we might get if we introduce the fluid with a low H on the shell side. So, we would like to prefer it to on the shell side. Next thing is liquid with the lower flow rate. Again, in this case we would prefer the shell side, provided the flow rate is such that it exhibits turbulent flow when it is flowing through the shell side. In case we find that even in the shell side it exhibits laminar flow, the Reynolds number is less than 200 for the shell side, then we would prefer to flow it to the tube side, because since the diameter of the tube or the cross sectional area of flow is less, so therefore the velocity, chances of the velocity being higher will be more. Suppose there is a fluid which has to be heated or cooled over a large range, say the delta T, the Th in minus Th out or the Tc in minus Tc out, this is greater than 40 degrees centigrade. In that case, you imagine that if that fluid is flowing through the tube, then in that case what happens, there is a very large temperature difference and the tube sheet which is holding the tube and both the ends are through the tube sheet. So, therefore, the tube sheet will be subjected to larger stresses. So, for those particular cases we would be introducing the fluid through the shell side. So, therefore, these are the, again I will repeat, these are the general guidelines. Based on this, since cooling water normally flows to the tube side, the minimum allowed water velocity is 1 meters per second. Generally, it is always higher velocity to decrease its fouling tendency. Fouling factor is also given here. Well, this is something very important that I should have mentioned earlier. So, therefore, now in this particular expression, you know how to calculate HO, you know how to calculate HI, you know everything, you can calculate UO. Once you have calculated UO, then using these particular equations, you can calculate A. But here there is something that I would like to mention. The entire expression has been assumed, rather has been derived assuming a clean tube. Initially, when you have started a new exchanger, definitely the tube is clean. But as time proceeds, what happens? There will be some deposit, some corrosion, something on the tubes, and as time proceeds, due to the dirty films on the inside and outside, what happens? If we have a tube here, there will be an additional resistance to heat transfer due to the deposits, etc. So, therefore, if you do not consider this, then what happens with time as these deposits form, they provide additional resistance to heat transfer. So, naturally, whatever heat transfer was happening in the new condition does not happen, there is decreased heat transfer. So, therefore, the heated fluid will not be heated to the extent that you want, or the cooled fluid will not be cooled to the extent that you want. If you want a heat exchanger to operate over a long period of time, then in that case you need to consider this particular factor, and or other which is known as the fouling factors you need to consider, and you need to incorporate them in the calculation of the design overall heat transfer coefficient, so that using this particular UD, the A that you calculate will be greater than the area which you are going to get without considering the dirt factors. And therefore, this additional A that you are going to provide will ensure that even with sufficient fouling, even with aging also, the heat exchanger will be able to provide the heat exchange that you want. The hot fluid will be heated to the extent that you want, or the cooled fluid will be cooled to the extent that you want. So, therefore, it is very important that when you are designing a heat exchanger, be it a shell and tube or a double pipe exchanger, we take up the design overall heat transfer coefficient. For this design overall heat transfer coefficient, it accounts for the dirt factor or the deposit on the inner side of the tube, and the dirt factor or the fouling factor on the outside of the tube. Okay. So, therefore, the UD, the U0 is corrected for with these two dirt factors in order to obtain the design overall heat transfer coefficient. Using this overall design heat transfer coefficient, we calculate the area of heat transfer. So, therefore, the expression of UD with RDO, RDI incorporated, when this UD is expressed in terms of AO, is given in this particular expression. It is quite evident that when fouling increases, naturally decreases the thermal efficiency, and there is one more important thing that you have to consider. It is not only that when fouling occurs, the heat transfer rate decreases, there is also other thing also. The pressure drop also becomes higher along with lower heat addition. So, therefore, it is much more important to consider fouling factors not only from the heat transfer point of view, but also from the pressure drop point of view. And it is also important, see, suppose you have to clean the tubes very frequently, that is not at all a desirable situation. Normally, tubes they are cleaned either by mechanical means or by chemical means. And so, therefore, we would always like to schedule the cleaning of the tube with the original shutdown of the heat exchangers. So, therefore, you need to remember two things. When you are taking fouling fouling factors into account, you are providing some additional area to the heat exchanger. This increases the capital cost of the heat exchanger, but at the same time you believe that you will be operating over a longer period and you will be saving on the expenses for cleaning. So, therefore, an optimum has to be struck between the capital cost and the operating cost in order to account for the fouling factors. Now, normally we find that quite naturally that when you have a higher fluid velocity, lower temperature, definitely the fouling tendency is low. And fouling, it also depends upon specific processes and presence of impurities. This is something very important for you to remember. For example, if you take naphtha from the crude distillation unit, you will find that there is very less aromatics there and the fouling factor is very less. But the same naphtha, if you take from a cracking unit, it contains a large number of olefins, and so therefore, due to the polymerization etc., they deposit on the surface, and under that condition the fouling factor is much higher. So, therefore, the fouling factor, it is taken, it is sort of a safety factor, it is taken just to guarantee a longer life of the heat exchanger without cleaning, and it is taken at the cost of increased capital cost, expecting that the operating costs are going to be less. Now, here what I have done is, I have just given you the typical fouling factors of certain fluids that are used. Again, remember just the example of naphtha that I have given, from that you know that fouling factor, it depends upon the specific processes, and so therefore, these are just representative values. These values can be taken for the design in order to get in order to ensure a longer life without cleaning of the heat exchanger. Well, the only one thing that is left is that initially I had mentioned that when you want to find out A, this is Q by U delta T LMTD, right. Now, to find out U, you have to find out HIHO. To find out HIHO, you need to know the DE, DI, etc., etc. you have to know. To start with, you do not know anything. So, how do we start the design? This is an iterative process. To find out A, you need U. To find out U, you need A. So, how to do it? So, therefore, what is provided here is some typical overall heat transfer coefficients in industrial tubular heat exchangers, including fouling factor, are provided here for say heat exchangers, for coolers, for heaters, for condensers, vaporizers, etc. These are provided. So, therefore, what you can do is that initially based on the application, you can select the overall heat transfer coefficient, some average between the minimum and maximum. Using that you found out A. From A, you can find out DI, DE, DI, L, etc. Once you have found these out, you find out HO, HI. Using this HO, HI, again find out U. See if the U, it falls within these limits or not. If they fall, you are lucky, then you can proceed with the design that you have done. So, therefore, these are just to start the design. Once you have done the design, you have found out AO. Now, you need to decide on the tube diameter and the tube length. Certain things I would like to tell you, there are some rules here which are again simply guidelines. For example, the minimum outside tube diameter should not be, it's actually 25.4 millimeters. The minimum thickness is equivalent to a schedule 40 pipe. So, the corrosion allowance is 3 millimeters. Such some guidances are there, based on which you can select the tube diameters. Again, remember, you have to refer to quotes to select the inner tube diameter and also to select the outer tube diameter. Generally, the lengths are also standard. Generally, they come in 6 meters or 3 meters length. So, therefore, once you have selected this, you can find out the length. The whatever length is there, divided by the length of each section, if you do it, then you get the number of hairpins that you require. Once you have found out the number of hairpins, then the next thing which you need to do is to find out the delta P on the tube side, find out the delta P on the annular side, and check whether these are respecting the limits which are provided. So, in the next class, we discuss the hydraulic calculations to find out the pressure drop. and we discuss a few other salient features of double pipe heat exchanger specifically and your tubular heat exchangers in general, and finish off the discussion on double pipe heat exchangers. So, till today we have finished off the thermal design of double pipe heat exchangers. We will be starting the hydraulic design in the next class. Thank you very much.